Hello, I'm Roman, and welcome to the new series of building convolutional neural networks from scratch in Golang. And this will be the series where the main target will be to build a simple neural network, simple convolutional neural network, and implement all of the required new layers from the scratch using the Golang. This series will be based on the previous series that's called Neural Networks from Scratch in Golang, and you can see that it's actually published on the YouTube. There are lots of the videos there. I used a book called Neural Networks from Scratch in Python, but implemented all of the things in the Golang. And I will be using the code that you saw in that video. So this is the repository. You can find it at roman.volkov/nfs_go. And I will build convolutional neural networks on top of this. I had a small break in between videos. I had a lot of things to deal with, and I actually posted a couple of the videos on the main channel. And I just wanted to take a small break from the live coding series. So we're getting back, and the goal of this video, if you remember, if you saw the previous series, you know that in the end, we've built a model that tries to do the classification for the fashion MNIST dataset. If you don't know what it is, I will show you. This is the replacement for this one. This is the replacement of the famous MNIST dataset. It used to be like, this dataset is usually used to challenge the architectures of the neural networks. They used to use the MNIST dataset, which is the dataset of the handwritten digits. But after the neural networks evolved, it became very, very easier to create a very simple neural network that will have something like 99% of the accuracy in just a couple of the layers and very fast training. So I think that was the Zalando, right? Yeah, so this is the Zalando. They released this dataset that we can use, and this is kind of more complicated than handwritten images. So the dataset consists of the grayscale images. I think it was 28 by 28 pixels for each image, grayscale, with 10 classes of type of the clothes. And in the previous series, we ended up having a model that can do the classification for these 10 classes. But what we did in the previous video series is a network of fully connected, or other way they call the dense layers, of fully connected layers that does the classification. And if I remember correctly, we had it the training. So this is how the model looks like. So this is the code for the training. We have this one. We have one layer activation. We have the second layer, not activation, and then we have the output layer with the softmax activation, and we use the categorical concentric flows and the categorical accuracy because we're building the classification for the categories, and that's it. And we trained it, and we had, if I remember correctly, we had a pretty decent accuracy, something like 90%. But one of the things, but since we're working with the image classification, there is actually a better way to do this, and that will be to implement a convolutional neural network. And the goals of the video today is we're going to take a look at what the convolutional neural network is, what is the convolution, and most likely we'll dive into theory only in this video, and then we can continue and build this in the next series. So let's go. I found a couple of the good articles, so we can take a look together, and this is the first one. That should be good to see. Nice image created by the author with the DALI. Okay, so table of the content. What are the convolutional neural networks, convolutional layers, channels, tries, biting, pooling layer, blah, blah, blah. Okay, so in general, convolutional neural networks, commonly referred as CNNs, are the special type of neural network designed to process and classify image. If you're new to this field, you might think, how is it possible to classify an image? Well, images are also numbers. We already knew this. Digital images are essentially a grid of tiny unit called pixels. So yeah, for example, this is the most likely an RGB image with the 3 channels. Each channel contains a pixel value, and then we blend 3 channels into 1 pixel value. Typically, each pixel is composed of the 3 values corresponding to the red, green, and blue. These values determine the color and intensity of the pixel. You can use the following tool, linear combination, sure it is, to understand how the RGB vector is formed. Yeah, but basically you could have this, you can represent it as a 3-dimensional cube or with 255 values per axis, and well, you will have the 3 axes in that case, and every pixel will have its own 3D coordinates. In contrast, in a grayscale image, each pixel carries a single value that represents the intensity of the light at that point, usually ranging from black, which is 0, to white, 255. So this is the example. And we'll actually be working with the grayscale image at first, but we will be building the convolutional layer that will support working with the RGB images. And once I figure out the fashionist datasets, I will look into more robust problems. So I will try to solve 2 problems, the classification of the grayscale image, and we'll think about something else, probably the classification of the RGB images, or maybe something different. To understand how the CNN function, let's recap some of the basic concepts about neural networks. Okay, that's, it's always good to recap some stuff because, the repetition is the mother of study, as I used to hear in my school. If you're reading this post, I assume that you're familiar with the basic neural networks. If you're not, I strongly recommend to read this article. If you are not familiar with this, I would highly recommend to go through the neural networks from scratch series, because we dived into the basic stuff about the neural networks using the book and kind of implemented all of the things with the code. But in general, we have the neurons, the most basic unit in neural network. They are composed of sum of linear function and nonlinear function known as the activation. So basically, the activation function and kind of controls if this neuron should fire or not. And there are different activation functions, and there are different ways how you pick up them, and it's not like there is a best activation function. It's all the matter of the model architecture. Input layer. Each neuron in the input layer corresponds to one of the input features. For instance, in an image classification task where the input is 28 by 28 pixel, the input layer would have 784 neurons for each pixel. Hidden layers, the layers between the input and the output layer. Each neuron in this layer is summed by the result. Hidden layers, the layers between the input and the output layer. Each neuron in this layer is summed by the result of the neurons in the previous layers and multiplied by nonlinear function. For example, In our case, like in the previous one, I think we have, yeah, for example, here, this is all the input, well, like the hidden layers, because I think when we have the finalize, yeah, this one, if you take a look, we're actually creating an input layer that is, well, empty, and the main purpose of this one is to actually hold the original data. And then we have the output layer, the number of the neurons corresponds to the number of the output classes. In case we're facing a regression problem, the output layer will have only one neuron, because in the regression we're actually returning a number between 0 and 1 corresponding to the, well, the probability. But in case of the classification, we'll have number of the output, what's called, number of the output neurons equal to the number of the categories, and each neuron will have the probability of this concrete class. For example, in the classification task with the digits from 0 to 9, the output layer will have 10 neurons. Each neuron, like each output neuron, corresponds to the, it will return the probability of concrete number. So for example, it's not like model 100% sure about the specific digit. Usually you will have some, for example, you pass the 9, which means that the probability of 9 will be very close to the 100 percentages, but the rest will be like very small numbers too. Once a prediction is made, a loss is calculated, and the network enters a self-improvement iterated process through which the weights are adjusted with the backpropagation to reduce error. Again, we have these two, so we have the train method. Yeah, and what actually does, we have some epochs, and we do. And for example, we have the forward method, which actually does the training or has the does the prediction. It's actually the same method. I mean, we using the same method to in the training, and then when we use the model, it's always forward. We just pass the input data and we get the output. But during the model training, we have a different thing, like addition, and that's backward method. And this is where we call, like, we go from the output to the input. We calculate all of the, this is where we calculate all of the derivatives against the input and against the adjustable parameters like the weights and the biases, and then we adjust the weights and the biases of the model, and then we kind of go back, we do this backpropagation, and then we go over and over. And this is how you do the forward pass. You calculate all of the derivatives during the backpropagation, you adjust the weights, so the model will fit the target data better and better. And this is like the whole training. Basically, the whole idea of the model training is that you're finding you're finding the combination of the parameters of the model, which is the weights and biases of all of the neurons, to fit the data that you're using as much as possible. That's it. So what you do is just going through all of the layers and calculate this. Now we're ready to understand the convolutional neural networks. The first question we should ask ourselves: what makes CNN different from the basic neural network? And I think the answer is the convolutional layers. There are fundamental building blocks of CNN. These layers perform a critical mathematical operation known as convolution. This process entails the application of specialized filters known as kernels that traverse through the input image to learn complex visual patterns. I mean, like, from what I used to work with the convolutional neural networks, I mean, I integrated them, but I never actually got like very deep into understanding the convolution itself and the math behind this. But in general, the idea of the convolution, and you can actually debug, like, this is the nice thing about the convolutional neural networks, you can actually debug the convolutional layers and see what features they extract. Features can be anything. For example, one layer of the convolution can find, I don't know, like horizontal lines. Another one would be find vertical or like round shapes or something else. Then the next layer of the convolutional will kind of combine those features and, for example, find something that looks like, I don't know, eyes or something else. And so what is the kernel? They are essentially small matrices of numbers, as well, actually everything in the neural network is just small matrices of vectors. These filters move across the image performing element-wise multiplication with the part of the image they cover, extracting features like edges, textures, and shapes. And kernel operation. So there is some kernel, there is an input, and it kind of offsets. Interesting how it kind of clamps it. I mean, I'm curious how it calculates those values on the edges. In the figure above, visualize the input as an image transformed into pixels. We multiply each term of the image by 3 by 3 matrix. This shape can vary, and pass it into the output matrix. I guess 3 by 3 is actually a size of the kernel, and you can change the size. And I think the bigger the kernel size, the more, I guess, accurate the convolution. But on the other hand, it will be harder to calculate it. So, but let's see. There are various methods to decide the digits inside the kernel. This will depend on the effect you want to achieve, such as detecting edges, blurring, sharpening. Interesting. So this is actually interesting. I mean, do we have some predefined kernels, like values, so I can use? Okay. Let's take a deeper look at this. Convolutional operation. The convolution operation involves multiplying the kernel values by the original pixel values of the image and then summing the result. This is a basic example of 2 by 2. So we have, we just multiplied the corresponding values, like 0 by 0, 1 to 1, 3 by 2, and 4 by 3. And then the output is, has the same size as the kernel, at least currently. Then we slice one pixel to the right and perform the same operation. So we have 1, so I guess then we have this slice 1, 2, 1, 2, 4, 5 multiplied by this one, and then we have 25. Then complete the first row and we move 1 pixel down and start again from the, okay? And it means that we have 3, 4, 6, 7, 3, 4, 6, 7, and the last one. The output matrix of this process is known as the feature map. Perfect, but how we understand how this operation works. But why it's so useful? We are just multiplying an added pixel, how we can extract image wizard by the, well, I mean, the whole neural network is just multiplying some values. And even with this one, it does some crazy magic from time to time. Now I won't be diving deeper into the convolution operation because I don't consider it to be pivotal for understanding convolutional nets in the beginning, but I will dive into it. However, if you are very curious, I will leave you what I believe is the best public answer to this one. Okay, so Okay, so this is the video for the 23 minutes, and probably it would be a nice video actually for the next video. So currently we'll just take a quick scan of what is the convolutional neural network is, so we would understand what actually we're going to build, and then we'll dive into this one. That's it. You have understood the most fundamental concept behind the CNNs, convolutional layers. At this point, you might be having a bunch of the doubts, at least I had them. I mean, we understand how a convolution works, but kernel always traverses through the image matrix one pixel at a time. What happens with the pixels in the corners? We are only passing over them one time. What if they are an important feature? What about RGB images? We started that they are represented in 3 dimensions. How does the kernel traverse over them? There are a lot of questions, but don't worry, we answer them. Okay, we'll start by understanding 3 essential concepts inside the convolutional layers: channel, stride, and padding. Okay, so all of this is actually about the image itself. The channels, as I explained before, digital images of 3 channels, but usually, yes, these channels could be very different. But okay, I guess in most cases we will work with a RGB image as well. For an RGB image, there are typically separate kernels for each color channel because different features might be visible or relevant in one channels compared to each other. That's true because some channels could be, for example, if you take a photo of the person and you will take the green channel, there will be like very little information about about the skin, etc. in the green channel, and actually a lot in, I think, mostly in the red, and a good amount of that information in the blue, because it just the how our skin looks like. There is not much greenish part of the colors like that you mostly see on the face or on the skin. This is why actually movies are recorded using the green screen, because it's much easier to separate green channel from most of the things that you record. Depth of the layer. The depth of the layer refers to the number of the kernels it contains. Each filter produces a separate feature map, and the collection of these feature maps forms the complete output of the layer. Wait. Depth. The output normally has multiple channels, where each channel is a feature map corresponding to a particular kernel. In the case of the RGB, we typically use one channel for each of the 3 matrices, but you can as many as well. For example, let's say that you have a grayscale image of a cat. You could create a channel specialized in detecting the ears and another in mouth. So we have the input. We have many convolutions detecting different things, and then I guess there is a polling. And this is actually the fully connected. The classification part this is what we built in the neural networks from scratch. So this is the fully connected of the dense layers. The only difference that right now as the input will use the result of the convolutions. This image illustrates the concept quite well. Think of each layer in the convolution as the feature map with a different kernel. Don't worry about the polling part for now, we'll break it down in a minute. Be careful with misunderstanding the channels in the convolutional layer with the color channels in the image. That was a representative example to understand the concept, but you could add as many channels as you want. But maybe don't call it channels. Each channel will detect a different feature in the image based on the values you assign to the kernel. So, like, I guess the output of the convolution would be like multiple like based on the number of the kernels, we could have lots of the different features, right? That's right. We have discussed that in a convolution, a kernel moves through the pixel of the image, but we haven't talked about the different ways in which we can do it. So that refers to the number of the pixels by which a kernel moves across the input image. Let's see the visual representation. Okay. The example, so before had the stride of 1, but this can change. So this is the stride 1, stride 2. A stride of 2 not only changes the way the convolution iterates over the input, but also the output, but making it smaller. So in that case, the stride is the number that we shift this reddish submatrix that we use to multiply by the kernel. I guess it looks like there is an input minus stride minus 1 for some reason, and this is the output result. Well, I'm not sure. A larger stride will produce smaller output dimension as it covers the input image faster, whereas a smaller stride result in a larger output dimension. So basically the smaller stride will result into the better feature detection, I guess, because it will, or more accurate. Increasing the stride will allow the filter to cover a larger area of the input image, which can be useful of capturing more global features. Okay. In contrast, lowering the stride will capture finer and more local details. Okay, so if we increase the stride, we can, I guess, understand like the pattern, like the global pattern. I know, for example, understanding the perspective of the image, like of the architecture. But if we lower the stride, which means increased, I would call it accuracy, or it's reduced. So we can understand things like, eyes on the image, I guess something like this. In addition, increasing the stride will control overfitting. Increasing the stride will control overfitting and reduce computational efficiency, as it will reduce the spatial dimension of the feature map. Okay, so I guess in the case of the overfitting, it means that if we'll have a very detailed convolution, it can, learn against very, very specific features that will appear only in this dataset, like very small details. And that means that this model could work very well on the training data, but decrease in the quality of the final on the unseen data. Okay, and the padding refers to addition of extra pixels around the edge of the input image. When you focus on the pixels in the image edges, you notice that we traverse them fewer times compared to those positioned in the center. The purpose of adding it to adjust the spatial size of the output of the convolution operation and to preserve spatial information on the border. I mean, this is so annoying. I mean, let's see another example with the CNN explain. Oh, nice. What is this? CNN explain a John convolution in your browser. Oh, what a nice website. I will take a look before the next video. Okay. Padding 0. Focus on the edges and count how many times this kernel is passing through them. Oh, so the padding goes outside of the image. So the white is the actual image, and this padding is kind of go outside. It means that, for example, this image in the top left corner, this pixel in the top left corner, will be used in computation like way more times than, for example, comparing to this one, where this top left pixel will be used only once. Now we're passing more times through the through the pixel in the edge and getting more information about this. In which case you want to apply padding mainly when the edges of the image contains useful information that you want to capture. You can increase the padding up to the kernel size you are using. And how does it affect the output field? Padding increases the size of the output feature map. If you increase the padding size while keeping the kernel size and stride constant, the convolution operation has more room to take place, resulting in a larger output because it adds more passive. The output size of the convolutional layer can be calculated using the following formula. So we have the output size, we have the input size, then we do 2 multiplied by the padding because we have, for example, top and bottom. So for example, there is a padding 1. It adds 1 pixel at the top and 1 at the bottom, 2, minus kernel size, which explains. So for example, the kernel size. So for example, here, if the kernel size is 3, we have 5 plus 0 padding minus kernel size. There should be plus 1, right? Yes, plus 1. Forgot. So for example, here it will be 5 minus 3 plus 1 will be 3. Here there is actually a situation with the padding, so it will be 5 plus 2 of the paddings minus 3 plus 1, which will be 5. Okay. Plus 1 accounts for the initial position of the filter, which starts at the beginning of the padded input. Okay. This is a visual explanation of the padding, but at a practical level, it doesn't have to be always the same on all sides of the images. The padding dimensions can be asymmetric or even have a custom padding design. Okay, so I guess you can have a padding like vertical, but not horizontal. No idea why do you need this, but okay, I'm not an expert. If you have reached this point, you can now officially say that you know how convolutional layer works. Convolutional layer, not the neural network. Nevertheless, this is not the end of the journey. There is a common misconception among beginners that convolutional layers are convolutional neural networks. It's true, because the convolutional layer is just only one of the layers. It's like to tell the same that the dense layer is the neural networks. Convolutional layers are essential component, but as its name indicates, there are a layer. We have comprehended the most important part of the CNNs, but there are still 2 other special types of the layers that we need to understand: the pooling layer and the flattering layer. Before explaining how it's crucial to have this clear. Although convolutional layer can decrease the output size, their principal objective is not dimensional reduction. The main objective of the convolutional layer is the feature extraction. So I guess it works like this. We have an image, we need to extract many features. I think can extract as much features as we want, probably combine them one into each other to have the complex features. And then we use the features to actually do the we use the features to train the model, to continuously train the model to do the categorical split, to understand, like, for example, which category contains which set of the features, something like this. I know, for example, in terms of the digits, like, for example, 9s and 6 will have something similar in terms of the features, like more, like rounded lines. But for example, when you compare it to the 7, most likely we would have more like a horizontal and diagonal lines, something like this. In fact, in most cases, we're not reducing the dimension of our data because we're creating new channels that weren't there before. So even if our feature map dimensions are smaller, we have more of them. Because we have the input, we have the feature maps that are much bigger. subsampling, and then we have the convolutions where we use features as inputs. Take a look at this example. Here we might be reducing a bit our feature map in each convolutional layer, but we're creating more channels. So as the result, we'll actually have more and more features that we can use for classification. What about subsampling layers? Those are polling layers, and its main objective is indeed dimensional reduction. How polling layers work. Imagine you have a large image and want to make it smaller but keep all the important features like edges and colors. The polling layer operates independently on every depth slice of the input. It recites specially using the max or average of the values in the window slide over the input. Okay, so we have the max polling and we have the average polling. Max polling, as I think the name suggests, takes the highest value from the area covered by the kernel. Average calculates the average. For example, we have the convoluted feature 4x4. For example, here it should be 7393. Okay, in case of the average, this will be 12 divided by 4, which is 3. This is 4 divided by 4, 1. This is 16 divided by 4, which is 4, and the same. So same convoluted feature could result into different what is it in different kernel, or what is into different polling, into different output of the polling layer. I don't know. In this example, we have reduced the feature map from 4x4 into 2x2. What is the difference between polling and the convolution operation? In polling, we're not applying any kernel to the input data, we are just simplifying the information with the math operation. So currently this is different representations of the convoluted feature in a smaller size, I guess. What about the channels? Polling also reduces the number of the channels. You must understand this. Polling layers do not reduce the number of the channels. They, I guess, reduce their size. Each polling operation is applied independently on to each channel of the input data. Let's see another example. Channels can be a bit complex to visualize at first, and I want to ensure that you understand correctly how they work. We have the image. So we have the convolution 9 by 1 by 1. We have 4. So this is the features. Then we have the max polling of 14 by 14. Then we have the convolution from this one into this one. And we have the final one. Okay. This is the good. I mean, on one hand, I understand this one, but on the other hand, I don't understand this. I mean, I don't understand how this feature that went through polling through another convolution can result into a more complicated feature extraction, so like a combination of the features. But I guess I will understand it once I will try to implement the CNN, or actually like the subsampling, and just debug it, because the cool thing about the convolution layer that you can dump it into the image, because currently this is the pixel values, right? And you can actually debug it and see what they produced. With convolution on polling layers, we can't reduce the number of the channels, just add more to existing ones. So we kind of adding them. Okay. So why and how do we combine all these channels? After convolution and polling layers have extracted relevant features from the input image, we have to turn this high-dimensional feature map into a format suitable for feeding into fully connected layers. Okay. Here's where a flattening array layers come into. Okay. Yeah, so this is, for example, I guess an example of what we had for, like, in our case that we did with the image classification based fully on the dense layers. Imagine you have a grid of the data. Okay, this half-flattering morph takes the entire feature map and reorganizes it into a single long vector. I guess it goes just rows by columns, 110, 41, okay. Although flattering changes the shape of the data, it does not make any changes to the actual formation. So we're going from two-dimensional array into one-dimensional array. That's the one that we actually used to train the model. Why do we need flattering? Integration of the features. By flattering the data feature maps into a vector, the network can integrate the specially distributed feature extracted for touch, such as classification. I think this is the main one. Compatibility with the dense layers. Fully connected layers are designed to operate on one-dimensional data, hence flattering is a necessary step to transition from the multi-dimensional tensors produced by the convolutional layers to the format. This is, actually the interesting part for me is how I'm going to represent the data for the convolutional layers, because currently under the hood of the dense layer, I'm using the GoNums math.dense struct, which uses like a two-dimensional array, and like usually the row represents the input sample and the values through the columns represent the input data itself. For example, in case of the input images, we have what we had, where is this? Okay, so we have the number of the inputs, and the number of inputs is actually in this case it's the image dimension. Okay, the x is the training data set. We take in the second one because the first one here will represent the number of the samples. Second one will represent the image itself, because if we take a look here, like this, and we have the image data. Now you can see that we append and load image returns the float 64 slice, which flattens the image from being a two-dimensional array into one-dimensional array. Anyway, why do we need dense layers in the CNNs? While convolutional layers are good of detecting features, dense layers are essential for integrating these features into the prediction. So I guess like this is the combination. Like I told you before, like previously in the one that I built before, the idea was to like dense layers try to build the prediction only based on the pixel values and kind of shuffle them somehow. But with the CNNs, we will extract the features first, and then we'll use features to do the classification, right? For example, if you design a convolutional neural network for facial recognition, early layers might detect edges and textures, while dense layers might interpret this to recognize the specific facial features without dense. CNN recap. Up to this point, we have revisited the whole CNN structure: convolutional, Boolean, flattering, dense. Dense we have, and everything that comes around the dense layers we already have, like activation functions that we used before. We have a couple of them. We have the optimizer. We have all of the things. So we could say that we join. What about the activation function and backpropagation? Yeah, because we need the activation to activate to decide if this part is activated or not, and backpropagation is kind of the crucial part of the model training, because during the backpropagation we'll adjust the weights and the biases based on the results. Yeah. You can check out this very interesting neurons backpropagation, convolutions backpropagation. Okay, I will take a look at activation function in the convolutional neural. So I think in the next video I will take a look at different article because we still need to understand the math behind, how we do the backpropagation. As in a simple neural network also need nonlinear terms in convolutional neural networks. Not all the layers we have seen have an activation function. Let's use an image as a reference to visualize it. Okay, so we have the convolution per Sorello. So pollen don't have the activation. The first pollen layers are not shown in this diagram. This is another way of visualizing the CNN. It doesn't mean they are not there. Just imagine a filter between shades. Okay. So it's actually convolution plus Sorello plus pollen. In the feature extraction part, the activation will be in the convolutional layers. The activations will be in the convolutional layers. The process is quite straightforward. After each convolution operation, you multiply the result by an activation function. So basically the same like we had with the dense layer. So we have color input, we have 3 filters by 3 by 3 size. And we have the activation function on, each of the output. And then we have the activation map. So we kind of merge it into one map. And then we use it for the max polling. Interesting that this becomes the input for the next convolutional block. Downsize activation map for max polling operation. Convolutional block. The pollen flattering layers don't have an activation function because, well, that's not the purpose. The pollen kind of reduces the dimension and kind of changes the data a little bit. The flattering is just a manipulation of the data. As we explained before, the main function of the we don't need to include non-linearities for doing this. Yeah, because we don't want to miss some part. Okay, the activations relo, we have it before, leaky relo. Activations output layer, sigmoid. This one we didn't use. I think we use only sigmoid. It's not commonly used in the hidden layers anymore due to the vanishing gradient problems, but it's still used for binary classification in the output, right? And that's it. Thank you, Mr. George Cardette. Hope that I read this properly. So, what is the result of this video? So, we took a look at very high level this description of what is the convolutional neural network is and what are the parts. We will for sure need to implement several things. So convolutional layer, pulling, flattering, at least. And then after this is done, we can combine it into the CNN to, for example, to solve the fashionist dataset. But those information is actually not enough for me to go deeper because we're still missing the math behind the convolution, and we're still missing how we're going to build the backpropagation, which is very crucial. So this is going to be the topic for the next video. I will take a look at this one. First, what is the convolution itself? Because we will need to implement this. I don't believe that... I'm not sure if the GoNum actually have the conv methods. Yeah. Conv... No, it doesn't seem that we have the convolution available. So I will have to implement the convolution itself. So it means that we'll need to understand how it has to be implemented, and we'll take a look at this video, and we will implement the convolution first as the operation on top of the Golang, and I will need to think actually how I should structure the data for the convolutional network. Well, for the convolutional layer, because currently we're passing, at least for the grayscale, we're passing the two-dimensional array where each row represents the input sample, and number of the rows represents the number of the samples in the batch. So I need to think how to structure it for example, for the RGB. I can go in one channel after another, and we'll just split that into for the convolutional layer, so it can work with the kernels. But let's see. I think this is going to be interesting. But for now, thank you for watching. Welcome to the new series, and as usual, you can check the Discord. We are having different conversations here. You definitely should check the previous series of building neural networks from scratch, so it will be easier for you to understand how I came up with this code. And yeah, see you in the next video. Bye bye.